Okay, calculus. This chapter 5 topics, this is the most recent stuff that we've done. But here you can see that it's highly represented. I pulled all these questions from that 2012 practice test. I renumbered them for you, but you can see that this is some popular stuff that shows up on an AP test. And that's not like some weird thing just because of this test. So, of course, all the stuff that we've learned in chapters, well, especially not so much limit stuff, but 3 and 4, all the derivative taking is big time at play here. All right, so this is good review stuff. Let's get into it. Let f be the function given by this. On which of the following intervals is the function f increasing? So, of course, we need to know that increasing means that f prime is positive, right? A function's increasing when its derivative is positive. So I'm going to take the derivative of that, and it's not a hard derivative to do at all. And then I'm going to set it equal to 0, so I can try to find the intervals where it's positive and negative. And I'm going to factor 3 out, and then that's 100 minus x squared. And yes, you have to do algebra sometimes in calculus class. And so it switches signs at -10 and 10. And there's different ways of doing this. You can like just pick numbers. You could think about like if you put in like a really big negative number, when that gets squared, it's going to be positive. So 300 minus something really huge is going to be negative. And then if you plugged in 0, you're going to get positive 300. And then if you plug in something big like a bazillion, then it's going to be just the same as this because squaring that. That's one way, just plug in numbers. You can also plug in numbers into this factored form of it. Like say, if you plugged in -20, then this is positive and this is negative. So that means that's going to be negative. Of course, the 3 is always positive, so you don't have to worry about that. Or you can say, hey, this is like a downward opening parabola. So it's going to have to go from like negative to positive to negative, if we imagine that way. So however you end up with these signs, where is it increasing? It's increasing when the derivative is positive, which is in between -10 and 10. So that be the answer. Let f be the function defined by this. What's the absolute minimum value of f? Absolute maximum value. So same game. I'm going to take the derivative. Same game because maximums happen when we go from positive to negative derivative, right, where it goes from increasing to decreasing. And they're talking about the absolute maximum, so I do have to think about what happens as x approaches infinity, right? Because like if you said, what's the absolute maximum of like y equals x squared, that doesn't have an absolute maximum because it goes up forever on both ends. So we just have to be careful about that because this is an option here. So let's see, let's do some quotient rules. So I have low d high minus high d low. The derivative of low is just 1 over low low. So that's 1 minus natural log x over x squared. Now if you want to find maximums and minimums, just like we did here, we're going to set that equal to 0. This is always positive, so that's not ever going to be equal to 0. So just the top, if you want like a rational expression, fraction, to be equal to 0, then the top's got to be equal to 0. So 0 equals 1 minus natural log x, or natural log x equals 1. So that's that happens at x equals e. If that's mysterious to you, then that's another one of these things. Like you need to know how to do that from pre-calculus, maybe a little bit at going back to algebra 2, but probably mostly pre-calculus. Natural log of x equals 1. Natural log is log base e. So this is the way to rewrite this without a logarithm is this to the this equals this. So x equals e to the 1. All right. So that x equals e is something, but I want to make sure that is in fact a maximum value. And we want, like, what is the value of the function? So this is like when we say what is the absolute value of f, that is a y value. The value of the function, those are y values. So e, this is an x value. If we wanted to know what's the actual value of the function, I'd have to plug e into this. So let's just do that real quick so we know what our possible answer is. If I plug e in this, natural log of e is 1 over x. So I'm thinking it's probably this, but I just want to make sure that this is, in fact, a maximum. So if we made our little sign chart, here's e. If I plug in, I can't plug in 0 because natural log of 0 doesn't exist, but I do know that as I get closer and closer to 0, the natural log function looks like this. It goes down to negative infinity. Right, so there's knowledge of limit stuff comes in handy there. So like negative huge number over a very small positive number. So this is going to be negative. Is that right? Yes. That is going to be negative. And then on the other side of e, if I plug in something bigger like, oh, I should be plugging things into the derivative. What am I doing? Sorry. I should be plugging things into this. So, sorry, 1 minus the natural log of x. If you take the natural log of things that are less than e, if you take the natural log of things that are less than 1, rather, then you get negative numbers. So this is going to be positive. If you take the natural log excuse me, of things that are less than 1, which is part of my territory here, then you're going to get negative numbers. So 1 minus a negative number is positive. And then if you take the natural log of something bigger than e, like e squared, the natural log of e squared is 2, so 1 minus 2, that's negative. So sure enough, it goes from positive to negative, and that's my answer. You got to watch out for when they ask for the actual maximum value. They're not asking for the x value where it happens. They want to know the actual value of the maximum. All right. Let g be the function given by this, where k is a constant. For what value of k does g have a critical point at x equals 2/3? What does critical point mean? That is a place where the derivative is equal to 0 or the derivative is undefined. And here, this is just like a x squared times e to the kx. That's not going to have any undefined issues. So we're looking to make the derivative equal to 0. So let's take the derivative of this. The derivative of this, I'm going to have to use the product rule, is the derivative of the first times the second. There's chain rule. The derivative of e to the x is e to the x times the derivative of what's inside. K is just a number, right? So that's how you take the derivative of that. Oops, you know what? I'm getting ahead of myself. I'm doing the product rule. So this is the derivative of the first times the second without taking the derivative of it first. Sorry about that. Plus the first times, and now I'm going to do the derivative of the second, like that. All right. And I want this to be equal to 0 when x is equal to 2/3. We want a critical point at x equals 2/3. So I'm going to plug in that 2/3. Here that gives me 2 times 2/3. I'm not going to try to simplify anything just yet. I don't want to get ahead of myself. Times 2/3 k plus 2/3 squared times e to the 2/3 k times k equals 0. All right, let's see what we can do here. I'm going to try to simplify the number parts. That's 4/3. And I'm also, there's an e to the 2/3 k here and an e to the 2/3 k here. So I'm going to factor that out. So 4/3 here, there's that factored out, plus This is 4/9 k equals 0. Okay, well this can't be e raised to some power. That can't be equal to 0. So this is the thing that must be giving me the, this is the thing that must be giving me the 0. So 4/3 plus 4/9 k equals 0. There's a lot of different ways you can do the algebra here. If you don't like fractions, I could multiply this whole equation through by 9. Multiplying through by 9 here, 9 over 3, that gives me 12 there, and plus 4k equals 0. So it looks like it's going to have to be -3. All right. The graph of the function f is shown in the figure above. For which of the following values of x is f prime of x positive and increasing? Okay, if for f prime to be positive, that means positive slopes. That happens from here to here and from here to here. So it looks like just places where f prime is positive, that it would be C and E are the contenders. What does it mean for f prime to be increasing? Well, if you want something to be increasing, that would be when the derivative of thing is positive. Derivative of this is the second derivative. So if you want the derivative to be increasing, that's when the second derivative is positive. That's kind of deep, worth pausing and reflecting on that for a minute. So what this is asking us, f prime is positive, means the function is going up, but f prime increasing means that the actual values of the slope need to be going up, which is the same as saying that the second derivative must be positive, and that means concave up. So that's what this is asking. They want to increase the first derivative positive, that means the function's going up, and derivatives increasing, which means concave up. So that happens here at E. All right. This is a graph of f prime. This is not the function. This is the graph of its derivative. The derivative of the function f shown above, which of the following statements must be true? F has a relative minimum at x equals -3. Well, right here, the derivative is going from negative to positive. So if the derivative is going from negative to positive, that means the slopes are negative and then the slopes are positive. That is a minimum. This is true. Does the graph of f have a point of inflection at x equals -2? Right here. No. This graph, if we didn't know what this was the graph of, if this was f, that's a point of inflection, but this is a graph of f prime. So if you're looking at a graph of the derivative, where do inflection points happen? Inflection points happen at the maximums and the minimums on the graph of the derivative. Right? When the slopes go from getting bigger slopes to getting smaller slopes, that is where we have an inflection point. So looking at this graph, that is where the original function f would have an inflection point. So that's not true. The graph of f is concave down from 0 to 4. So here, if this is a graph of f prime, then the slope of this these are the slopes of this. The slope of the slope, that's the second derivative, is negative. Now that is true. So 1 and 3. If you're wondering what that noise is in the background, my doggy is here with me today. And probably wants to go outside, which we'll do in a minute when I'm done this video. And I promise you no dogs were harmed in the making of this video. He's a good boy. All right, so use your calculator. So, okay, I got my calculator ready. If f prime is equal to this, then f has a local maximum at x equals, okay, so maximum, just going back to this graph, this one would have had a maximum here. If we're looking at the graph of a derivative, we need the derivative to go from positive, which is like going up, increasing, to negative. So if we can find a place where the derivative, which is this, goes from positive to negative, then we found a maximum. So let's graph this. Square root of x to the fourth plus 1 plus x to the third minus 3x. And then it looks like my answers range, they're in order here, so from, let's say, like -3 to 2. So I don't want to look more than that. So I'm going to say -3 to 2, and then that negative. That's probably fine. Go ahead and graph it. Remember, we need a place where the derivative goes from being positive to negative, right? Increasing to decreasing. So it's right there. It's in between 0 and 1. Looks like I have 2 contenders. It looks like it's definitely less than a half. But you want to be sure. We don't find that. We're looking for a 0 on this. Now, don't be faked out. If you're hearing like, oh yeah, I'm looking for a maximum. But this is the graph of the derivative. So we're looking for a 0 where it crosses from positive to negative. Calculator is just a stupid machine. So it's right between that left bound and this right bound. Yep, 0.350. Let's see. Oh, use your calculator. Got it right here. Let the function with first derivative, so I got a derivative again. Which of the following are all the intervals on which the graph of f is concave down? Let's make the graph, and then we'll think about, well, let's talk about it first, because let me bring this page back. So on the graph of a derivative, the second derivative is the slopes of this, right? The prime of f prime. So concave up is where this is going up. Concave down is where this is going down, right? Because this is the graph of the derivative. So if we're looking for where it's concave down, that's where this is decreasing. All right. And we got a nice little interval for us to graph it on. So let's get rid of that last one. At e to the x to the fourth minus 2x squared plus 1 minus 2. And I'm going to go to my window and just graph it from negative 1.5 to 1.5. So remember, we're looking where this is decreasing. So it looks like from negative 1.5 to around negative 1, this is looking good, and then 0 to 1. So you can check those values. Now, how would you actually check to see those? Like, how do you know where this is? Well, that's a minimum of this, so you could go in and find the minimum there. It's somewhere between, well, I can use the little cursor thing. Don't draw on your calculator screen. It's not a good idea. And there's a left bound and a right bound for my minimum. And if it's negative 1, then I think we're good to go with that answer. Yep. Why does the calculator say this? Because it doesn't know how to do calculus, really. It's just doing numerical approximations of everything, and it's usually a little bit off, but not so much that we can't tell what's up. All right, so that. All right. The graph of f prime. Geez, they really like this, huh? Make you look at a graph of f prime, and then you got to answer questions about that. That's a hot topic. It's something you need to know how to do, calculus students. Graph of f prime, the derivative of f is shown in the figure above. the function f has a local maximum. Okay, so this is exactly the same stuff. This is all from the same AP test, so like obviously this is something that's very important. So a maximum is where the derivative goes from positive to negative, right? So where does this go from positive to negative? It goes from positive to negative right there. That is where it has a maximum. This, if you pick this, that is the sucker answer. Nobody is going to ask you. You're a senior in high school taking a college level math class. Nobody's going to ask you, hey, where's the maximum of this? Oh, there it is. I've got two kids who are 9 and 11 who don't know anything about calculus. And I could show them this and say, where's the maximum? And they could point to that. So nobody is going to ask you that, ever. Like, where's the maximum? Oh, it's there. No. If you find yourself doing something like that, you got to second guess yourself. Hold on, hit the brakes, think about what you're looking at, because it ain't going to be that. All right, this is a graph of a second derivative. So this is a graph of the values of the second derivative. So that means here, these are negative. So whatever the original function looks like, it was concave down here because these are negative. And then from here to here, it's positive. So it's concave up. And then here, these are negative, so that means it's concave down because these are the actual values of the second derivative. And then here, it must be concave up. Where are all the intervals on which the graph of the function is concave down? Hey, that turned out to be exactly the thing that we needed to do. So it's concave down from -2 to -1 and from 1 to 3. You know what the sucker answer is? The sucker answer is for the person who looks at this and go, oh, I know about concave up. Look, it's concave down right here. See? Concave down from -1 to 1. Yep. No, that's not asked. This is not the graph of f. This is the graph of the second derivative. No, this is the sucker answer. Sucker born every minute. Don't be a sucker. All right. Let f be a polynomial function with values of f prime of x at selected values of x given in the table below. Which of the following must be true? So this is kind of like those other problems that we're talking about, except the values of f prime are given in a table instead of a graph. All right, which of the following must be true? The graph of f is concave up. That means f concave up means the derivative of the derivative is positive, right? F double prime is positive, which would mean that the values of the slope must be increasing. And that's clearly not true because it goes from 3 down to 1 and then from 7 down to 5, so that does not need to be true. The graph of f has at least 2 points of inflection. Inflection points are where the derivative goes from increasing to decreasing or vice versa, where the slope of the derivative changes. And it's going down here and then up here and down here. So I think this has to be true because the values of the slope, if we were going to make a picture of this, let's see, -2, 3, 0, 1, 3, 4, 5, 7, 6, 5. So however it does this, if this is a graph of f prime, it goes from decreasing to increasing. There's got to be an inflection point. That's not necessarily it. It could hit it before or after, but it's definitely going from down to up somehow. So like in that answer, is f increasing the whole time? All of these values of the derivative are positive, which might make you think, yeah, f's increasing. But we don't know what's happening in these gaps. This could go from -3, down to -1 or something, and then back up to 1, somewhere in between here. We don't know if it does or doesn't do that. So this could be true. It's definitely plausible considering those numbers, but it doesn't have to be true. This does have to be true because you can't go down and up again without having a minimum in there. And a minimum on the derivative is an inflection point. F has no critical points. It could. That's what we're talking about here. It could dip below 0, and if it did, that would be a critical point. So we can't see, obviously, that it doesn't have to have any because these are all positive, but it could. And we're looking for things that must be true. F has at least 2 relative extrema. Relative extrema are maxes and mins, remember. And that doesn't have to be true. It could have none, right? If the derivative stayed positive all the time, then it would be some version of increasing all the time. So that doesn't have to be true. And we were right. It's B. And, I think that's it. That was the last one.